video is on question 1. Define fluid. A fluid is a liquid or a gas. Question 2. State the equation for density rho. Density is equal to the Greek letter rho, which is total mass divided by total volume of an object, has units of kilograms per meters cubed. It's a scalar. Question 3. Determine the volume of 1 kilogram of gold. The density of gold is approximately 19,300 kilograms per meters cubed. So we'll take this equation for density. We're going to solve for volume. We know the mass is 1 kilogram. We were given the density of gold. Question 4. What is the density of pure water? Include units. So this is the density of pure water. It's 1,000 kilograms per meters cubed. Question 5. What is the average density of salt water? Include units. So the average density of salt water is a little bit more than that of pure water. It's about 2.5% more density of salt water than pure water. Question 6. What is the average density of a human body? Include units. It's about 1.01 times 10 to the 3 kilograms per meters cubed. So what does that mean? That means the human body will float in ocean water because the density of a human body is less than that of ocean water. Question 7. Will it be easier or more difficult to swim or stay afloat if the density of a human is greater than salt water? Why? It will be more difficult if the density of a human is greater than salt water because a dense human would naturally sink to the bottom. So thankfully our density is less than salt water. Question 8. Do dead bodies in the ocean salt water float or sink? Why? Dead bodies in the ocean float since they are less dense than ocean salt water. Question 9. Does oil in the ocean float or sink? Why? Oil in the ocean floats since it is less than ocean salt water. Question 10. Does metal like gold in the ocean float or sink? Why? Metal in the ocean sinks because it is more dense than ocean salt water. Question 11. A dead fish is floating in the middle of the polluted radioactive ocean. Label the forces on the fish. So you have the buoyant force pushing upward, and you have the force of gravity pulling downward. Question 12. State the equation for pressure P. So pressure P is force per unit area, has units of newtons over meter squared, which is equal to a Pascal. Pressure is a scalar. So if an object is under a fluid, then its pressure P is P equals P sub 0 plus rho GD. So take a look at this image. If we're under the water or a liquid, then the pressure at point P, a vertical distance below the liquid, is the pressure of the air at the surface. That means at the water level, plus rho GD, where rho is the density of the fluid, G is 9.81, and D is the depth of the object under the fluid. Question 13. Is it a good idea to wear high heels on grass? Why? It is not a good idea to wear high heels on grass because the pressure from the heel of the shoe is great enough to sink the high heels. Because the high heels have a small area, therefore there would be a greater pressure on the heels. Question 14. The surface area of 1 foot of a 65 kilogram man is 0.02 meters squared. Calculate the average pressure each foot is applied to the ground. So pressure is force per unit area. This is a mistake. This should say 65 kilograms here, not 12. So 65. So fix this part and you're going to get a different answer. Question 15. A heavy chair has a mass of 12 kilograms. Each of the 4 legs has a surface area of 4.50 centimeters squared. Calculate the average pressure each leg applies to the ground. So pressure is force per unit area. The numerator is the force of gravity. The area is the area of the 4 legs of the chair. Question 16. State the meaning and equation of the buoyant force, the force of buoyancy. So the buoyant force is the upward force when placed in a liquid, when an object is placed in a liquid. The buoyant force is equal to the weight of the displaced fluid. So force of buoyant equals rho GV, where rho sub F is the density of the fluid. In this image, it's the blue liquid. G is 9.81 meters over second squared. V is the volume of liquid displaced. So on the left sphere, V would be 4/3 pi r cubed. On the right sphere, it would be 4/3 pi r cubed times 1/2, because only 1/2 of the sphere is under the water. Question 17. 60% of a 60% of a cube with a side length of 1.25 centimeters is under fresh water. The cube does not move. Part A, calculate the upward buoyant force acting on the cube. So we're just going to use force of buoyant equals rho GV. And for V, we have a 0.6 here, because it's 60%, it's under the fresh water. And we're going to convert centimeters to meters. Part B, calculate the downward force of gravity acting on the cube. Well, the cube doesn't move, so force of buoyant up equals force of gravity down. You could say the buoyant force takes the place of the normal force if there was a surface, a hard surface. Part C, calculate the mass of the cube. Well, just solve for G. Just solve for little m and we could solve for the mass. Question 18, state Archimedes' principle. Archimedes' principle is the buoyant force from the previous equation. The buoyant force is equal to the weight of the fluid it displaces. So take a look at this previous problem and then you'll understand Archimedes' principle. Question 19, state the meaning and equation for Pascal's principle. So when an enclosed fluid, a change in pressure is transmitted to all parts of the fluid in the walls of the container. So take a look at this image here. Pressure 1 equals pressure 2. Pressure is force per unit area. Work done on object or area 1 is equal to work done on 2. Work is FD. Question 20. According to Pascal's principle, in a hydraulic press, a downward force on an area will result in an upwards force on another area. Suppose a downwards force of 135 newtons on an area of 1.25 meters squared results in an upward force of 325 newtons. The surface areas are at the same height. What is the surface area A2 which rises? So A1 and A2 are at the same height. So P1 equals P2, pressure is force per unit area. And we could solve for A2. Question 21. According to Pascal's principle in a hydraulic press, a downward force on an area will result in an upward force on another area. Suppose a downward force of 135 newtons on an area of 1.25 meters squared results in an upward force of 325 newtons. The vertical distance between the two surface areas are 2.25 meters. What is the surface area A2 which rises? The density of the fluid is rho sub fluid equals 0.8. So we have this equation now. See how it's a bit different from the last equation. And we could just solve for A2. Question 22. Define a fluid in hydrostatic equilibrium. Static equilibrium means a fluid which is not moving. Hydrostatic equilibrium means water which is not moving, because hydro means water. So recall the conditions for static equilibrium. If sigma f equals ma and sigma f is 0, the left hand side, then the right hand side a is equal to 0. If acceleration is 0, v is 0. For static equilibrium. For dynamic equilibrium, V is constant and not 0. Question 23. Define laminar flow. During laminar flow, there was a smooth, even flow in fluid and layers which do not mix. The streamlines are smooth and continuous. If the speed of the fluid increases, then there will be turbulent flow. During laminar flow, the velocity of the fluid at a point is constant versus time. So laminar flow is the image on the top. These are also called streamlines. Question 24. What do streamlines tell us? Streamlines tell us the direction a fluid will flow. So streamlines do not cross each other. If the streamlines are closer to each other, then the fluid is moving faster. Like I said, these are streamlines. This top is called laminar flow. This bottom image is called turbulent flow. Question 25. What are the characteristics or conditions for an ideal fluid? We got constant velocity, incompressible fluid, constant pressure, no viscosity, no internal friction in the fluid, and steady flow. So this image has streamlines, which are blue. Question 26. State the continuity equation. Define each variable and draw and label an image. Okay. So this is a continuity equation. For two different cross sections, you have A1 V1 equals A2 V2. A is a cross-sectional area, V is the speed. So you can also call this equation the volume flow rate Q. The units on each side is meters cubed per second. So look at this image below. Since A1 is greater than A2, that means V2 is going to be greater than V1. Now, if V2 had the same speed as V1, that means there would be a buildup of water. And the water, or a fluid, then the fluid keeps going back. But this is a continuity equation. So if there's going to be no buildup of fluid, once the fluid reaches A2, it's going to have to move faster. Now look at this image below. A2 is greater than A1, so V2 has to be slower than V1. The speed of the fluid needs to decrease so there's no gaps in the fluid. If V1 is equal to V2, then there's going to be a big air gap in the fluid. Question 27. A liquid with a density of 1050 kilograms per meters cubed moves to the right with a speed of 3.25 centimeters per second through a tube with a cross-section area of 4.75 centimeters squared. What is the volumetric flow rate of this liquid in meters cubed per second? So Q equals AV. And that's the volumetric flow rate. Question 28. A liquid with a density of 1050 kilograms per meters cubed moves to the right with a speed of 3.25 centimeters per second through a tube with a cross-sectional area of 4.75 centimeters squared. The cross-sectional area of the tube then increases to 6.25 centimeters squared. What is the speed of the liquid as it flows through the larger tube in meters per second? So I use a continuity equation and I just solve for V2. Question 29. A liquid with a density of 975 kilograms per meters cubed moves to the right with a speed of 4.25 centimeters per second through a tube with a cross-sectional area of 2.75 centimeters squared. The cross-sectional area of the tube then decreases to 2.25 centimeters squared. What is the speed of the liquid as it flows through the smaller tube in meters per second? We're just solving for V2. And in 28, we're also solving for V2. Question 30. State Bernoulli's equation and define each variable. This kind of looks like the law of conservation of energy, yes? Instead of mgh, we have rho gh. That means we divided this by volume. So mass per unit volume is rho. Instead of 1/2 mv squared, we have 1/2 rho v squared. So if this was mass, and we divide by v, mass per unit volume is rho. So it looks like these two things on the left side, you divide them by volume, and you get mass per unit volume to get density. So this is pressure. So this must have units of pressure. And this must have units of pressure. Okay. So pressure on the left side equals pressure on the right side. So remember this, high pressure means low speed, and low pressure means high speed. So example 1, a fluid flows through a pipe, let A1 equal A2. So water goes to the right, a fluid, then it goes down and it continues to go to the right. I'm saying cross-sectional area 1 is equal to cross-sectional area 2. So looking at this equation, if A1 equals A2, then V1 is equal to V2. Because remember the continuity equation. A1 V1 equals A2 V2. So 1/2 rho V1 squared on the left side cancels with 1/2 rho V2 squared on the right side. We know H1 is greater than H2 because H1 is above H2. So if H1 is greater than H2, then P2 has to be greater than P1. Okay, so here we go. Here's another example. Now A1 is greater than A2. This is a large volume, a large cross-sectional area. Then the fluid goes through a smaller cross-sectional area. So if A1 is greater than A2, then that means V2 is greater than V1. Bam. So H1 is greater than H2. So rho GH1 is greater than rho GH2. And 1/2 rho V2 squared is greater than 1/2 rho V1 squared. So now we can determine a relationship between P1 and P2. We're not sure which one is greater, P1 or P2. So There are many questions where you will use both the continuity equation and Bernoulli's equation to solve for an unknown. So we have to know this equation, and we have to know A1 V1 equals A2 V2. Question 31. A circular pipe with a varying diameter is shown below. The diameter of the circular pipe at point 1 is 18 centimeters, and the diameter of the circular pipe at point 2 is 8 centimeters. If the pressure at point 1 is measured to be 225,000 pascals, point 2 is a vertical distance 65 centimeters above point 1. A liquid of density 975 kilograms per meters cubed flows up the pipe with a flow rate of 0.555 meters cubed per second. Calculate the pressure at point 2. So Q1 equals A1 V1. So we're going to find the speed of the fluid through point 1. Then Q2 equals A2 V2. Now we're going to find the speed of the fluid through point 2. So now we know the speed of the fluid at point 1 and at point 2. We know the pressure at point 1. We know that the change in height is 65 centimeters. So we're going to use this equation. Just write down the Bernoulli equation. Let's solve for P2. And we know H1 minus H2 is 65 centimeters, and convert that to meters. And then we know 1/2 rho V1 squared minus V2 squared. This here I highlighted V1 squared minus V2 squared. My final solution is negative. Question 32, state the Bernoulli effect. Bernoulli's effect uses Bernoulli's equation when H1 equals H2. The fluid is flowing horizontally. This is also called the Bernoulli principle. So you could see the difference. From Bernoulli's principle, we can see that a decrease in pressure means an increase in speed and vice versa. Question 33. A liquid with a density of 975 kilograms per meters cubed moves to the right with a speed of 4.25 centimeters per second through a tube with a cross-sectional area of 2.75 centimeters squared and pressure of 195,000 pascal. The cross-sectional area of the tube then decreases to 2.25 centimeters squared. What is the speed of the liquid as it flows through the smaller tube in meters per second, and the pressure in pascals? So remember, A1 V1 equals A2 V2. That's the continuity equation. Then we're going to use Bernoulli's principle. And we're going to solve for P2. Question 34. Describe how the Bernoulli effect relates to the pitot tube to determine the speed of an airplane. So you have wind, you have air moving to the right. This air goes through this tube, down A, and it pushes this fluid down. And if we could determine delta H, we could find the speed of the plane. So Bernoulli's equation tells us this. V sub A is equal to 0 meters per second. Because the speed, the wind just hits this part and it stops. H sub A is about H sub B, which is not equal to delta H. So this is delta H here. So we're going to use this equation here. So if we could solve for delta H, we know rho and G, and we could just solve for V sub B. V sub B is the speed at which this wind goes to the right at point B. And like I said, at point A, the wind just hits this part of the tube and it stops. So that speed is 0. Question 35. Use the Bernoulli equation and the continuity equation to determine the difference in pressure of a fluid in the throat of a cylinder if we are given the radius R1 and R2 and the speed V1. So this is called the throat of the cylinder. So beginning with the continuity equation, we get this. V2 is in terms of V1. Now use the Bernoulli equation, which is this. We'll say the height at H1 is equal to the height at H2. So rho g H1 goes away. And we're going to substitute this here. And now we're just going to solve for P1 minus P2. P1 minus P2 is equal to delta rho gy. Sorry, rho g delta y. Which is equal to this. Then we could factor. And this is delta y here. Question 36. Determine the initial horizontal speed of a liquid pouring out of a hole from a container as shown in the figure below. So if the vertical height at H is really big, there's going to be a great pressure. So this water is going to move horizontally a lot. If H decreases, the water doesn't move so far horizontally, it's just like a little bit. So beginning with the Bernoulli equation, and I spelled beginning wrong, I'm sorry. We have this. We're going to say the pressure at A is equal to the pressure at B almost, because these are both pressures from the air. V sub A is about 0, since this speed is going to go down much slower compared to B. And HA minus H sub B is equal to H. So if we put all of that into here, we could solve for V sub B, about 2GH square root. 37. Define viscosity. Viscosity is fluid friction within the fluid itself and its surroundings. So example, cold honey and cold syrup both have high viscosity because they move slow. Question 38. State the meaning of and give the equation to Stokes' law. Stokes' law tells us the drag force of a spherical object with a smooth surface when it feels when moving through a fluid with laminar flow because of its viscosity. So the drag force is 6 pi nRV. N is pronounced eta. It's the Greek letter eta. It's the coefficient of viscosity of the fluid. The thicker the fluid is, the slower it flows, the bigger the eta. R is the radius of the sphere. V is the speed of the sphere traveling through the fluid. Don't worry about how to derive this equation here. So if an object is going down, the buoyant force points upward, the drag force points upward, and the force of gravity points downward. I'm saying positive y is up. So buoyant force is rho GV, 6 pi eta RV is up, and mg is down. 39, define turbulent flow. Turbulent flow is faster than laminar flow. During turbulent flow, the flow is chaotic and there are eddies. During turbulent flow, the velocity of the liquid at a point fluctuates versus time. And turbulent flow is much more difficult to analyze than laminar flow. Question 40, state the meaning equation and define each variable for the Reynolds number R. So if the Reynolds number is small, then there is laminar flow. If Reynolds number is large, then there's turbulent flow. So this is the equation for Reynolds number. VR rho over eta. So if R is greater than 1,000, then we have turbulent flow. If it's less than or equal to 1,000, then we have laminar flow. So take a look at this equation. If VR and rho are big and eta is small, then we're going to have turbulent flow. If VR rho is small and eta is big, then we're going to have laminar flow. And don't worry about how to derive this equation.